Hello everyone. In this video, we will begin to examine topic 9.5, the Doppler effect. In particular, we will examine the Doppler effect for sound waves and light waves, sketching and interpreting the Doppler effect when there is relative motion between the source and the observer, describing situations where the Doppler effect can be utilized, and solving problems involving the change in frequency or wavelength observed due to the Doppler effect to determine the velocity of the source/observer. So, the Doppler effect is an effect that most people are familiar with, although they may not know the name. This is the effect that occurs when you hear a car or any kind of object, sometimes a train gives the same effect. When it's coming towards you, it makes a certain sound, a certain pitch. And then the moment it passes you, that pitch changes. So it's sort of a wee-oo kind of thing going on. When it's coming towards you, that sound is different than when it's moving away from you. The change in the observed frequency is how we quantify that change in sound. And it occurs when there is relative motion between a source and an observer. So in this diagram over here on the right, I've shown the source of the sound moving, but the observer could be moving as well, or both could be moving. The important aspect for the Doppler effect is that you get it whenever there is relative motion, when the two of them are moving relative to one another. So with sound, I've already mentioned that the thing that changes is the frequency directly, and that corresponds to pitch. As we'll discuss later, there is also an equivalent of the Doppler effect for light or any electromagnetic waves. And in that case, the frequency shifts, just as before, corresponding to the color of the light or the wavelength of the light in non-optical wavelengths. For the Doppler effect, we will first analyze the case of a moving source with a stationary observer. That's the first one that I just mentioned. But as mentioned before, you could also have a stationary source and a moving observer. So the source of the sound is staying put, whereas you, the listener, are moving past it. You will hear a similar change in frequency, although they cannot be analyzed in exactly the same way, as we will see. So, focusing in on the Doppler effect for a moving source and stationary observer for sound, we first want to explain why this occurs. And it's actually fairly straightforward to see why this occurs with an appropriate wavefront diagram. And the general idea is that as a source is moving, if we see this source represented with the green dot, it's emitting waves, and the stationary observer is going to detect those waves. But as you can see here, the key element of what is going on is that the center of each successive wave, so the center of each wavefront, is going to be where the source is at every point. Now, where the source was when the first wavefront emitted was around right here, and you can see that it's sort of equidistant from that point. So that first wavefront is right there. But then the source moved a little bit, and when it moved, the center of the second wavefront moved with it. As a result, that wavefront is sort of bunched up against the leading edge of the first wavefront, and so on and so forth. And so what you get is sort of a whole bunch of wavefronts bunched up over here in the direction of the motion of the source, and sort of more spread out wavefronts in the opposite direction of the movement of the source. And so we can ask ourselves the question, how does the observed frequency depend on the velocity of that source, the thing that is sort of moving the center of those wavefronts, and the emitted frequency? So that'll be our central question. But before we get to that and analyze it, let's take a look at sort of a moving simulation version of the same thing. All right, so here we have a GeoGebra simulation. Our source is shown as a blue dot, and an observer is shown on the right. And I'll let it play, and you can see that that blue dot moves to the right, and the center of each successive wavefront, okay, moves with it. And you can see that the end result is that the wavefronts end up bunched up together, close to one another, in the direction of the observer. So the observer here is measuring a frequency, in this case f prime, that is higher than the frequency of the source. And if you had a source moving away from the observer, so in this case we're just going to put an observer on the other side of the motion, that observer is observing a longer wavelength than they would otherwise, and that corresponds to a lower frequency. And the analysis of this will be dependent on us understanding that it's because that central source is moving that we get this differential effect on the wavefronts, on the wavelengths. Notice that from the perspective of each particular wavefront, they just propagate outwards, moving outwards in all directions. So they're not tilted in any way. It's only that the center is moving that makes the whole sort of structure seem tilted. All right, so our first analysis here is how does the observed frequency f prime depend on the velocity of the source us and the emitted frequency? All right, so to understand this is the case we're considering, and we are considering a moving source and stationary observer. So the diagram we're going to focus in on looks like this. Our observer is right in the middle, our source is right in the middle, that's S, and we're going to consider 2 points. The very first wavefront it emits, and then the very next wavefront it emits. So those are 2 particular points. Now when it first emits a wavefront, it does so right here, and that wavefront ends up at A and B at the same time. So you can see that A and B make sort of a semicircle arc. You could draw the whole circle if you wanted. A and B are where that wavefront ends up 1 period later, when the next wavefront is emitted. But that next wavefront is emitted at S prime over here. Okay, so that's what this diagram is showing us. The velocity of the source, us, is here. And so the observer located at B, notice this is moving towards / detected at B, right? This is the observer, will detect a wavelength lambda prime. And lambda prime is going to be shorter than the original wavelength. The original wavelength can be seen to be here. It's just that distance between S and A, or for that matter, S and B. Whereas lambda prime is the detected wavelength between the current placement of the source, because that's where the next wavefront will be emitted, and B itself. So this distance right here is the detected observed wavelength. So let's take a look at how to calculate that. If they have a shorter observed wavelength, lambda prime, then what is lambda prime equal to? Notice, lambda prime is equal to this distance minus this distance. So we're going to calculate that. That first distance right here, that's the original wavelength, and that's equal to v, the velocity of the wave in the medium, that's how fast the wave moves, divided by the frequency. And notice that is just using the standard v equals lambda f relationship. That's for the wave in the medium, and this v right here is not the velocity of the source. It's the velocity of the wave in the medium. So that's v over f minus, now we need this distance. What is that distance? That distance is us, the velocity of the source itself divided by the frequency. So this distance right here is us divided by the frequency for 1 period later. All right, well that gives us this distance minus this one. All right. One way to think about that, in case you didn't follow that, is that this us divided by f, that's a lot like saying us times t, the time period. So the speed of the source times the time period is this term. Those are equivalent because t is 1 over f. So now we stick those together. We say, all right, lambda prime is v minus us divided by f. So to find the detected frequency, right? This is the observed frequency, not the emitted frequency, but the observed frequency. We can then say that that's equal to the velocity of the wave in the medium, okay, divided by the observed wavelength, what we just calculated here. So we plug that in. We say that that is v, and 1 over lambda prime is this equation inverted. So you take v times f divided by v minus u sub s. So v times f divided by v minus u sub s. That's just some algebra. And you can see that initial dependence on f here, f prime is this thing, okay, algebraically removed, times f. So it's v over v minus u sub s divided by f. Now, why did we do that? Didn't we already have lambda prime? Well, lambda prime was not written in terms of the original wavelength. So what we want to know is how f prime depends on the original frequency and then the other variables. Notice that if the velocity of the source increases, then f gets progressively larger because us is getting closer to v. Special things happen when the velocity of the source gets bigger than the velocity of the wave in the medium. You get what's called a sonic boom, and we will discuss that at a later point. But for now, this is the fundamental relationship for a moving source and stationary observer for moving towards B.